routing basics. So there are typically multiple IP subnets or multiple IP networks on a typical data communications network. Layer 3 devices are required to exchange data between these IP subnets. These devices have the routing capability and can forward data across subnets. Routing is the basic element of data communication networks. Again, it is the basic element, it is the core element. It is the process of selecting paths on a network along which packets are sent from source to destination. So in this chapter, we introduce routing, and we expect you to understand the basic principles of routers. You need to know how routers select the optimal path. This is what is going to make you an engineer. You need to understand the contents of the routing table, and you need to master advanced routing features. Please notice the term is master, not just passing. Okay, so let us look at the overview of routing. What are the basic concepts? What exactly is happening? So in a typical network, we have multiple layer 3 devices, as you see. So in this case, we have network N attempting to communicate to network M. And you can see there is a multiplicity of network devices, layer 3 network devices along the way. These are all IP capable devices. They have their own IP addresses. This network is completely independent from this network. So there needs to be routing. Are we together?
Yes.
This router here needs to identify a way to reach this router here, because this router is aware of this network and this router is aware of this one. Now, in order to be able to reach that network, this router needs to know that when it receives data for this network, it needs to send it to this next hop, new term. Next what? Next hop. Or this next hop, because that is also another path. Anyone sees that? We can pass here.
True.
Or we can pass here. So this router needs to know that it can either send to this next hop or it can send to this next hop. What is it going to depend on? Now the routing protocol is going to determine that. Are we together? We can see in this case we have 2 routes. But are they even only 2? Are they only 2? Does anyone see this route here? Anyone sees that route?
Yeah.
Does anyone see this route here? Anyone sees that route? All different paths are called routes. It is actually routes, isn't it? They are routes to the destination, but we call them routes, you know, maybe just to create some difference with English. And that is what we are talking about here. So we have router 1, we have router 2, we have router 3, we have router 4, and they are interconnected. So we have network N attempting to talk to network M. And we can see that this interface here will be the gateway for network N. And this interface here is the gateway for network M. Because ultimately, when network N finishes sending the packet to network M will need to do what? To reply. So when network M is replying, it will also send to its own next what? Next hop. So you can see this is the gateway for M talking to N. This is the gateway. This is a next hop. This is a next hop. Okay, this is the destination. But now, for N talking to M, this one is the gateway. This is the next hop. This is the next hop. And this is the what? The destination. Now, these routers have something that we call a routing table. And it is the one that contains that information. Are we together? The information that we call the routing what? Information. And this is the information stored in the routing table. 3 main pieces of information we need. 3 main pieces of information we need. we need, where are you heading to? What is your destination? I'm trying to reach 10.1.1.0/24. Okay, what is your next hop? Where are you sending the packet next? What is the exact, and any of you did relay? You remember those relay races?
Yeah.
Yes, when you have a field and then you have 2 of you here and another 3 of you here, another 3 of you here, another 3 of you here. All you have to do, it starts from here, you're running that direction, you only need to run up to the next point. You hand to that guy. He runs up to the next hop. He runs, do you remember that stuff? This is how routers operate. You know, if you're the first runner and you're the best and you run all the way to the end, your team will not win, isn't it? It will not win. In the same way, the people here must know that you're running that direction. Because if you run and give it to him and he runs back and gives it to you, then you will still not win. Are we together?
Yes.
So everyone in the path must have a routing table. They must know where to hand the stick next. Who do I give the stick to next? And that is going to be the next hop. So in our case, if this router 1, attempts to speak to this network, the next hop will either be this one, or both, as we shall see, if it is what? A load balanced network. Now, the destination network is where you're heading to. The next hop is whoever you hand the packet next from yourself. The outbound interface is the interface directly connected to the one you're handing your packet to next. Now, please notice that in this case, we could also have this entry. Okay? And the outbound interface is still gigabit Ethernet 0, 0, 0, but the next hop is 1.1.1.3. We can have both entries and have what we call a load balanced what? Network. So if you have any packet, splice it into 2 and send a bit there and a bit there. It makes it faster for you when you're transmitting information. We shall look at that when the time comes. Now we want to break this down and see what exactly exists. So let us look at this network. In this network, we have 4 routers. We have router 1, router 2, router 3, and router 4. Each router has its own network connected to it. What we like calling a stub network. And then we have the intercommunication network in the middle where the routers pass the data if they want. Now, look at the routing table. In this case, we are looking at the routing table of router what? Router 2. So in router 2, this is the 11 network. It has that if you want to reach the 11 network, send your information to 2.2.2.2. See 2.2.2.2? That is the only way you reach the 11 network. And 2.2.2.2 is on interface gigabit Ethernet 0/0. We shall see why this interface is important. We shall see why it is important. Now, and then if you want to reach the 13.0.0, you will see that we have to send to that guy. Have you seen it?
Yes.
The next hop must be directly attached to you. Now, sometimes the next hop is indirectly attached to you, and you need to reach the next hop through routing again, and we shall see how that happens. Now, routers manage path information by managing this thing here. In fact, this is the tool of a what? Of a router. This is what it needs to forward packets along the what? Along the path in the network. So how do these entries come about? How does this router even know that to reach this network, I need to send here? Because this network is not directly attached to it. How does it know to reach this network, it needs to send here? You know, it can easily know that to reach this network, it is this side because it is attached to it. But how did it know? How did it know? How did it know to reach this guy? That is what we want to look at. How do they generate the routing table? And there are basically 3 ways to get routing information. First is direct what? Routes. Direct routes, as I've mentioned, are those ones that are directly attached to us. Look at this router, for instance. This network is directly attached to it. Also, this network is directly attached to it. So it is going to have, how did you learn it? It's directly attached. Okay, what is the destination? 10.1.1.0. That is this network. Okay, what is the outbound interface? He is connected on this interface. I know because I feel him. He's on me. I mean, I'm so sure this is the what? The path to go. And then, okay, cool, I agree with you. So what else do you know? I know about 20.1.1.0. How did you know about him? Protocol. He's directly attached to me. How do you reach him? It's attached to this interface gigabit Ethernet 0/0/1. One of the ways we learn routes is through direct routes. The networks are directly attached to us. Now, another way is the one I illustrated earlier, through static routing. Some engineer went in the router and told it that in case you want to reach 30.1.1.0, you just send your packets to this interface or send your packets out of this interface. That is what we have here. Someone typed in the router that if you want to reach 30.1.1.0/24, just send your packet out of this interface. Send the packet that direction. It will reach. For you just send, remember we said IP is unreliable. It's connectionless. So with this rule, IP doesn't check whether this network actually exists, nada. For him, he just needs to know that there is something connected on gigabit Ethernet 001, and if there is something, he will send the packet. Other troubles will be performed by that what? That router. Is anyone following with me?
Yes, yes.
Yes, that is what it means. It is connectionless. Now, you can see this is static. Some engineer went in and typed in, if you want to reach this network, said, now we can specify the interface, or we can specify the next what? The next hop. Now, this, sorry, not this hope, not this hope. We need to be hopeful because people are in a struggle, but we mean this hope, okay? Not the other hope. All right, so static routes is the second way. The first way we learn routes is through direct what? Routes. Now, the third one is dynamic what? Routes. Dynamic routes are the ones we learn through routing protocols, such as OSPF, such as intermediate. OSPF is open shortest path first, intermediate system to intermediate system, routing information protocols, enhanced interior gateway routing protocol, border gateway protocol. We use these routing protocols to reach the destination. So these routing protocols can learn remote routes automatically. In this case, for instance, this router has learned a way to reach the 40.1.1.0/24 network. Then we ask, man, how did you learn it? I learned through open shortest path first protocol. He taught me that if I want to reach this network, I know that guy exchanged some information with that guy. I don't know what they talked, but finally he told me I just need to send out of this interface if I want to reach that network. Now, listen to me carefully. Listen to me what? Carefully. Of these three, if you were a router, which one would you trust more?
First one.
The first one, I would also trust this one most. Okay? I would also trust this one most because it is directly attached to me. Okay? Now, if we had only these two, which one would you trust most?
Static.
Pardon? Static.
That's static.
Dynamic.
Dynamic. Okay. We shall see. Me, I don't know. We shall see. So, with direct routes, I have already explained. They are directly what? Attached. So the router just reads Like the example, if you remember Dan's question at the beginning, these are the kinds of networks most people have in small enterprises. You have your local area network that side, and it connects to the internet that side, just two networks. Now, in that case, you're most likely not going to configure any routing because there is routing in the router since they are both direct what? Routes.
John.
Yes.
By directly connected, does it include any wireless connection?
Yes,
Or
yes, yes, and yes plus 4.
So they can be directly connected wirelessly.
These can be wired or wireless.
Okay.
Actually, right now as you speak, most of you have made your phone a hotspot.
Yes.
Eh? Now, there is a bit of something else, but I'm not going to explain it in this class because of time. The GSM moving to this other network, but let us consider it to be wired. Your phone is getting internet from your line, wired, because the line is directly in the phone, right?
Yes.
And then it is connecting the internet to your wireless card, wireless network interface card, and your laptop picks it. There are two networks. Did you configure any of them in your phone?
No.
No, because they are directly what? Attached. But now, if you make your laptop, listen carefully, because you can do this. If you go to your CLI and make your laptop also kind of a server, a router, and then you connect now your laptop via cable to another laptop, you know this laptop can transmit internet to that laptop because it has got it from the what? From the phone, isn't it? Now, in this case, there is a possibility that this phone does not know this network because the network it gave to the laptop is on that direction. The IP address on this direction could be your own IP address or an automatic IP address. So you might want to set up a route on this laptop if it needs to reach that side. And on this laptop, tell it for anything you receive, just send there. Are we getting the idea?
Yes.
We are doing this every time, only that most of us are using softwares to do them. But ladies and gentlemen, when you install that software, that exact thing I've explained is what it is doing. And you can do it in your CLI. You can do everything in your CLI and everything will work like magic. All right. So, remember I've told you direct routes are learned because they are directly attached. What does this tell us about direct routes? If the interface goes down, Daniel goes with his daughter to work, and the daughter says, "Hey, Daddy, you see this wire?" And she plucks it out. The route will disappear from the routing table because the only reason it was there is because it is directly attached, but now it has been plugged out. Are we together?
Yes.
When the interface goes down, the direct route will disappear. Now, considering that we can have, let me see, yeah, sure, here. Considering that we can have two different paths, let us say there is another router here. I'm now modifying. Okay? Excuse me. There's another router here. And then we have this path, and we also have this path where we send to 1.1.1.3. Which one do you think is the best one?
The app on 1.1.2.
The question is why?
It is closer. It involves only one router.
Hey, what if this network is in Mutukula? What do you mean by closer? If it is Mutukula, it is Mutukula.
There are
It
no,
is directly connected to the
there are
router.
no middle.
Okay, there is only one hope.
Hmm.
There is only one hope between the source and the destination, isn't it?
Yes.
Okay, yeah, cool. That's okay. But now, we are thinking RIP, as we shall see later on, we are thinking RIP. But for now, what I wanted to highlight is that we want to look at how do routers select the best what? The best path. What do they depend on? How do they consider? Yes, for now, for us, we are saying that, just that one is nearer. Let me ask you a question. Who should I ask?
Me, Zaifa.
Okay, Huzaifa.
Yes.
Huzaifa, where do you stay?
Where you get it?
Where you get it? Where you get it? Let me see. Yeah. Now, we want to talk about optimal route selection. What do you base on? What does the router depend on if it has different paths to reach exactly the same destination? What does it base on? What does it consider? That is what we want to talk about. But before we do that, let us examine the routing table. When you want to check for your routing table in ENSP, you display IP routing table. That's the command. Let us look at the routing table. These are the entries you'll find. These are the entries you'll find. The destination and its mask, subnet mask. The protocol, how did you learn a way to reach that destination? Now, the preference is a ranking method for protocols. Does that make any sense? Guys, I need you to be extremely with me here. Does that make any sense?
First, repeat on the preference.
Preference is a ranking method for the protocol. It is the trustworthiness. Yes, I've told you we have direct, we have static, we have dynamic. In dynamic, we are going to particularly talk about OSPF. Okay? So 3 ways to learn a route. 3 ways to learn a route. Now, trustworthiness. How much do you trust each of these? For direct, ENSP attaches trustworthiness of 0. The lower, the more trustworthiness. So for direct, we trust it 100% because it is directly attached to what? To us. So you can see the preference of direct routes is what? Is 0. Are we together?
Yes.
For static, we attach 60. For OSPF, we attach what? 10. So we trust OSPF more than static routes. Why don't we trust static routes? Because static routes are not dynamic. If someone comes tomorrow and changes the router, which is in the next hop, the static route will not adjust. It will remain the way they typed it. So we don't trust it. Are we getting the idea?
I'm not getting it.
Okay.
Because what you are saying is like saying even direct someone can come and disconnect that thing connecting it.
No, look at this network. Are you seeing this network?
Yes.
We have a destination network here and a source network here. Someone came to this router and configured that to reach the destination, send to 1.2. The destination network here, okay, is actually, let us say this network, this very network. Let us say it is 2.0/24. Someone came here and said to reach the 2.0/24, send to 1.3, which is this interface. Yes?
Yes.
And then after 3 days, a senior engineer comes and says, wait, who told you to call this network 2.0? This network is supposed to be 3.0. So they change the IP address here and the IP address here. Are we together?
Yes.
But this is probably a router in Mukono, and this is a router in Jinja. This one where they put the route is a router in Kampala. This router will still have that to reach 2.0, send here. Is there a 2.0 anywhere on the network?
Yeah. It's not there.
But if it was OSPF or any other dynamic routing protocol, it will learn that 2.0 that does not exist. It will either update the entry or it will delete it. Are we together?
Yes, yes.
So that is the problem. And the other thing, static routes do not even check of the actual existence of the destination. When you type this in here, whether or not, let us say it was 2.0, and by mistake you type 20.0, that is what will go there. The entry will be there the way you see this one. Now for dynamic routes, it will sometimes tell you the network does not exist because you didn't type them in. OSPF checked which networks are connected and it advertised them in the network. Do you get the idea?
Yes, yes, yes.
Yes, so we trust OSPF more than direct. That is the preference. So if it was an OSPF land route here, it would have 10. Are we together?
Yes.
But now these are default preferences. Now the cost is exactly as it sounds. The cost, let us say in RIP particularly, it's called metric. How far is that network according to you? So the cost can be any number, but it is basically a way to tell how distant a distance. Think of it as a distance measure. Preferably, I like to think of it as a cost, an actual cost. So the lower the cost, the better the what? The route. How much do you pay to reach that destination? Are we together?
Yes.
Now for different protocols, they consider different things to determine the cost. Now for flags, for now, which is not exactly supposed to be under this coverage, but for now, think of flags as a way you got to know, a way you can reach your next hop. Okay? A way you can reach your next hop. Are we together?
Yes.
It is normally D or it is R. When it is D, it's for direct. When it is R, it's for recursive. Now, direct means my next hop is directly attached to me. Recursive means if it is R, to reach my next hop, I have to go through another routing protocol. Or I just learned my next hop through someone else. Is not directly attached to me. The interface is the networking, the interface on you that is attached to your next hop, or that is in the direction of your destination. Which interface will you send the packet out of to reach the destination? That is the interface, the outbound interface. So those are the fields in our routing table. If they're a bit confusing to you, don't worry, you're going to be looking at these fields every time. Okay? So these are the fields I've just explained. You have them in the notes I uploaded, so you can as well go through them and read for yourself. So route preference. What are the basic concepts? This is how we compare routes. Please note that if we have more than one route, okay, more than one routes, greater or equal to 2 to the same destination, then we have to select one. Are we together?
Yes.
If we have more than one, then we have to select one. And how do we select? We have the routes, they have the destination. If the destinations are different, just install the routes in the routing table. If the destinations are the same, start by looking at the what? The preference. Start by looking at how exactly, how much do you trust the protocol? How much do you trust the person who told you? Who told you? Someone configured in me. What if that guy made a mistake? Aha, that one it is 60. How did you know? OSPF, OSPF. Yeah, this guy just advertises. It must be a network that is somewhere out there. Okay, 10. How did you know? He's attached to me here. He is attached to me. That one 100%. We trust that one 100%. Are we together? So let us say you learned of 2 different routes to the same destination. One of them was directly attached. One of them was static configured. You will choose the one which is directly attached. Is anyone with me?
Yes.
Yes. That is what preference is. The higher preference is the one we shall install in the what? Please note that we don't install all the routes we have learned. We install only the optimal routes, the best routes. Are we together?
Yes.
Yes.
Okay. So what is the comparison process? Dynamic routing protocol, OSPF has 10, static has 60. So you will see that we shall install the one with what? With 10 to our routing table. In other words, someone got in this router here and entered a static route. Said if you want to reach the 10.0.0.0 network /30, send to 30.0.1.1.2. And then someone configured OSPF in here. Now OSPF looked at its stuff. There is a way it works, we shall see. It examined itself, sends hello package, did what, and then it figured, this one is the next hop. We shall only install the OSPF route in the routing table. We shall not install this one. Please note that in case the OSPF route goes down, then we shall install this one. It is somewhere floating, waiting. Are we together?
Yes, we are together.
Good. Now, what if both routes were actually having the same preference? Maybe there was no OSPF. Some engineer came in and configured that in order to reach the 10.1, send to 30.1.1.2. And again configured in order to reach the 10.1, send to 20.1.1.2. What happens? What happens? What do we do? If the preference is the same, because in that case they are both static routes, they will both have preference 60, then we are going to consider the metric, okay, the cost. But for this case, because for static routes, they normally have the same cost unless you configure some cost or you differentiate the preference. By the way, you can get one of your static routes if they were both static, and you set one for a higher preference like 80. They will not install it. They will install on this one. This one will come in if this one fails. This one is actually called the floating static route. We're going to talk about that. Now, let us say they are both OSPF. They are both OSPF. If they are both OSPF, it means both of their preference is what? Is 10. Now, in this table, we have not shown the preference, but we know that since they are both OSPF, their preference is what? Is 10. Now, look at this network carefully. The cost along each link is what? Is 10. How many links do we go through to reach this network if we pass that direction? Can someone be in class?
1.
2.
Yeah.
How many links do we go through to reach here if we pass that direction?
2.
1.
2. We go through this link and that link.
1.
Link, not router. Link, not router. And even if it was router, we go through this one and go through this one also, isn't it? How many links do we go through if we pass this direction?
1.
We pass only through this link, or we pass only through this router. So each link is 10. You pay 10 shillings for each link. When you pass that side, you will pay 20 shillings in total. When you pass this side, you'll pay only 10 in total. Which one will you take?
10.
I'm assuming that none of you is extravagant to choose an expensive path over a cheap one. Okay? We shall take the cheap one and then we reach much faster. These are the default preferences. These are the default preferences. I've talked about them already. Direct is 0, static is 60. OSPF for internal is 10. Now, all the OSPF we are going to be talking about in this course is internal OSPF, but there is also OSPF external. For those of you who want to join the professional level course, we shall talk about this one, but that one is 150 because we don't so much trust it as the internal one, especially considering that we don't have authority over the external network. Are we together?
Yep.
So this is now the total selection process. You have routes to a certain destination. Are they different? If yes, just put them in the what? In the routing table. If they are the same, look at the preference first. If they are the same, look at the preference first. The one with the higher preference goes in the routing table. If the preference is the same, look at the metric next. The one with the lower metric goes in the what? In the routing table. Are we together?
Yes.
Yes.
If,
Now,
and if
please
the metric
note,
is the same.
pardon?
If the metric is the same.
We do load balancing.
Okay.
Okay? Now, there are other things that we can configure, but for now, let us say we do load balancing. There are a lot of other things we can configure to differentiate this stuff. Now, here we have talked about preference, and we have talked about what? Cost or metric. Now, I want to specify to you that there is the very first thing we look at. The longest what? Match. Now, I don't know how to even explain this. But let me try. So, we have in our routing table that to reach, we have a network on that side of the router, 10.10.10.0/30. Okay? And on this router, we have a route that says to reach 10.10.10.0, excuse me, to reach 10.10.10.0/24, send to next hop A. To reach 10.10.10.0/28, send to next hop B. To reach 10.10.10.0/30, send to next hop C. To reach 10.10.10.4.2, excuse me, .2/32, send to next hop D. Now listen to me carefully, okay? On this network, there is a computer 10.10.10.2. Are we together?
Yes, sure. Good.
Daniel,
Yes.
are we together?
Yeah, we are together.
Daniel, do you notice that 10.10.10.2 is an IP address in all these networks? This one, this one, this one, this one.
True, but the subnet is different.
Yes, the subnet is different. But remember when you come on your host here and you say ping, 10.10.10.2. Do you specify a subnet?
No.
This router is looking for 10.10.10.2. It doesn't know that it is /30 or /24 or /2 or /. Are we getting the idea?
Yeah.
I don't know that you guys are with me here.
I'm lost.
You're not lost. You think you are lost. When you go to a computer and you say ping 10.10.10.2, you specify a host address. You don't specify a network. Are we together?
Why have you said that it is? Why did you conclude that it is part of all of these networks?
When you list IP addresses in this network, this one will be there. When you list IP addresses in this network, this one will be there. When you list IP addresses in this network, this one will be there. When you list IP addresses in this network, this one will be there. Isn't it?
Yes.
Yes.
Hey. Now, normally, Dan, Samson, Fred, Cephas, Doreen, everyone in class, normally, the router will only select /24 because it knows this IP address is there in this network. It is not because you specify the network. Are we together?
John.
Yes.
John.
I need you guys to understand this. Yes, Uzaifa.
No, I just want to get it more clearly. Like which example of a host which wouldn't be included in this, which wouldn't be part of any of these ones?
192.168.4.11.
Yeah.
Hey.
Okay, thank you.
Okay, but just to simplify and give you a straightforward answer, think of 10.10.10.121. This one will not be there. I hope you guys can follow with me. Will not be there in this network.
Yes.
Yes.
It will not even be there in this network.
Yes.
He will not even be there in this network.
Yeah.
So there is only one route to him. Are we together?
Yes.
10.10.
Now this is where subnetting becomes important. For those of you who are enjoying the numbers. 10.10.10.42 will not be there in this network. It will not be there in this, it will not be there in that one. But our particular destination address is there in all of them. In fact, when the router looks at its routing table and sees these routes, it knows that it can use any of them to reach this destination address. Because you're not reaching a destination network. You want to reach, the only reason the router sends to a destination network is because it knows this address is in that network. So if they told me to send here, that router should be knowing because that address is in that network. Are we together?
Yes.
But now there are 4 different places where that address is. Now in this case, the router will select the route with the longest match. The match goes from 0 all the way up to 32. Are we together?
Yes.
Yes.
So in this case, it will select the 4th what? Route. Are we together?
Yes.
Yes.
It has the longest match. Now, when we say same routes that we have been talking about, select preference, select metric, we are assuming the longest match is the same. If there is a difference in the longest match, it will always first choose the longest match. Are we together?
Yes.
It doesn't matter whether this one was learned through static, and this one OSPF, and this one direct. It doesn't matter. It will choose the longest match first before it looks at the preference. Are we together? Now,
Yes, we have
if the match is the same, the length, if the net mask length is the same, now it will look at the what? At the preference. If the preference is the same, now it looks at the what? At the cost or metric. Is that clear?
Yes.
These things here, for those of you who have not gone to enterprise engineering, these things have caused a mess in enterprise engineers. Say, I can't reach, I want it to pass the other side, but it is passing here. And yet I've changed the OSPF preference. I even changed the metric. It has just refused to work. The problem is there is one with a better match. Are we together?
Yes, yes.
It will always select the longest match first before it looks at the preference or the metric. Now, by saying same route, what we actually mean is ECR, equal cost routes. Okay? Equal cost routes is what we mean. It is the same. It is the same what? Actually, not equal cost route. Equal cost routes lead us to load balancing. It is the same longest match, excuse me for that. When we say same route, we mean the longest match or the length of the subnet is the same. If the length of the subnet is different, we shall always choose the longest length, period. Okay?
Yes.
So, we assume the first thing it will check here is the subnet length. But by seeing same routes, of course, it can't be the same route when they are different lengths, right? By saying same routes, we are assuming it is the same what?
Same length.
But if they are different lengths, for the last time I say it, it will always select the longest what? Match. So now, let us look at the route-based forwarding, which I've already mentioned that uses the longest what? The longest match. I have explained that thoroughly, I hope. Okay? And we also have an example of the longest match here. You can see here, we are attempting to reach this IP address. It is the destination. Okay? Do we notice that that IP address is part of this network?
Hmm?
Yes?
Yes.
Now those people who didn't understand IP addressing are feeling like, no, and there are other things for him to teach.
We shall learn
This
slowly.
network, this IP address is there in that network, and it is also there in this network. But it is not there in this network. But you see that this one has a length of 16, this one has a length of 24. It will select 24. Oh, by the way, for your information, we can even add a route with a destination of 0.0.0/0 network. Now, this route matches all destinations because it has the shortest one and it is an any network destination. That IP address is for any network. But as we can see its longest match, irrespective of which protocol learned it, it is going to be the last one selected because it has a lowest what? Match. So if we have 10.10.10. something to the same destination, they will choose that one. Unless there is no one else. That is when we look at this one. That's why we call it a default what? Default route. In case you fail and there is no other way, just send everyone to that guy. This is another example of the longest match. Okay. It is the only one, so it's going to be, oh sorry, so it's not the only one. When we have .3.2, this one matches and this one matches. But this is 16 and this is 24, so we shall select the 24. Are we together? Hey.
I'm all right.
Yes, we are.
Sudan is exactly up here.
Okay. So let us look at the route-based forwarding process here. Let us look at the route-based forwarding process there. Here, we are trying to show you the routing table of R1, the routing table of R2, and the routing table of R3. We have this destination network, and we have this source network. The source is trying to reach that what? That destination. Now, router 1 will check his routing table, okay, and see that the destination is listed there. He sees the next hop is 20.0.1.2, and the next hop can be reached by sending out of this interface there. So he will send the what? The packet. Router 2 will receive the packet and sees the destination is 40.0.1.2. Looks into his routing table, says 40.0, here it is. Then he sees the next hop is that one. How do I reach the next hop? Just send your packet out of that interface. It will encapsulate the packet and send it out of that interface. Router 3 receives the packet, and then it sees this one might have learned this through static or through OSPF or ISIS. This one might have learned through static or OSPF or ISIS. But this one will learn it because it is a what? A directly attached what? Route. So you learn it through direct protocol. So you will have it listed here, and the address is right there, or the next hop, and we'll send it out of that interface. So you will send the packet out of that interface, and it will reach the destination. Now the reply will move the same. Now for the reply, please note that the destination network will be what? Are we together? Are we together?
Yes.
Yes, so this one, when it receives the reply, it will check its routing table, see the destination network, and the next hop. This next hop is here. Sorry, yes, the next hop. Sorry, this one, yes, outbound interface. The outbound interface for this one is this one. So it will send the packet out of there to its next hop, which is that. Okay, this one will check his routing table, see that the destination next hop is this guy here, and the outbound interface is that guy there. So you will send the packet out of here. This one will receive and see that it is directly, that is directly attached. The outbound interface is that one, it will send the packet. That's how communication will occur. Are we together?
Yes.
When a router receives a packet, it searches its routing table. So let us talk about static routing. Let us talk about static routing. But I've already done a lot of talking about static routing, right? Why don't we just do it? Should we?
Yes.
Yeah.
Yes.
Let's just do it. Let's just do it. Let's just do static routing this time. We have done a lot of talking. So I'm going to switch my screen to that, and then I'm going to set up 3 routers here. I'm going to set up that, and that, and that. And I'm going to, let me align them nicely. And I'm going to connect, this is router, okay, I'm going to call this Kampala router. I'm going to call this Mukono router. And I'm going to call this Ginger router. I'm going to connect them together, gigabit Ethernet 00 to gigabit Ethernet 00, and then gigabit Ethernet 01 to gigabit Ethernet 01. Like that. Cool. And I'm going to, let me extend this a bit. I want to reduce the size a bit. Okay. And then I'm going to have a switch here. And a switch here. So we have a network at Ginger and a network at Kampala. Mukono is just a transit network. So I'm going to have some 2 hosts here and some 2 hosts here. This is your exercise, by the way. Later on, you will also do this. I'll connect this to 1 and connect this to 2 and connect this 24 to 2 here. I'll connect this 2 to 24 here. I'll connect this to 3 to 1 and connect this to 2. Connections done. I'm going to start up everything. This is switch 1.
John Peter.
Yes.
Why are you connecting the router to port 24 of the switch and simultaneously on the other side? Can't you use the port 1?
No, I can. I can even use port 11. And I can even use 24.
Because
so I've used 24.
Okay, fine.
No, I don't know whether I've answered you. What I'm trying to say is you can use any port depending on your plan.
It's okay.
Yes. So me, according to my plan, I've put all hosts on ports from 1 and I've connected all uplinks because this port is called the uplink port, connecting above me. I've put them on the last port in the network. So if these were in my rack, it is easier for me to identify where the router is connected because I might not be seeing the router cable direct. Maybe I'm using some patch cables and other stuff. So it is easy for me to know that 24 on all my switches connect to routers. But basically, you can connect anything.
Because most people
go ahead.
prefer using the gigaport 1 and so forth compared to any other port.
Yeah, true. What I'm trying to do here is to tell you that there is actually no reason why. The only reason why is your plan. If you have your plan, that's it. There is no rule, but it's normally advised that you're supposed to be uniform. Like in this case, I've used 24 for all uplink. Now it is easier to notice. And then I have not used a middle port for the router because I don't want PC1 to be on port 1, then PC2, port 2, port 3, port 4. Then the router is on port 5, then PCs from 6, 7, 8. It looks bad. You get it?
True.
Yeah, so, but it all depends on your plan. I normally preferably want to have things that are a bit uniform. So you see, I've connected the hosts to 1 and 2. Even if I'm enforcing port security or STP on my switches, I know 1 and 2 are ports that are connected to hosts. I know 24 is connected to a router. Later on, you will see when you log in to configure, you don't want to be coming to check. So when I open my switch, I know that 24 is on the router. I know that 1 and 2 are on hosts. That's it. So it is easier for me even to memorize.
Okay.
Yeah. All right. So I'm going to have a 10.0.0.0/24 network here. For most of you, I don't know. Let me do this, just so we don't get any confusion. For most of you, this thing is going to be in some kind of green color. Okay. So I don't know if that would lead anyone to confusion, but let me just use.
But green is not visible. It's not clear.
Okay. So you prefer black?
At least, or any other color that can be red.
Okay. Actually, when I'm doing my own simulation, I always just use white. So let me choose white. I always just do it this way. Okay, that's going to be 10.0.0.0, and this is going to be 10.0.1. Preferably, let me use the one I normally use for labs. This is going to be router 1, router 2, router 3. So my networks are going to be 10.0.1 to 2.0. Because this is a network between router 1 and router 2. Does that make sense? This one is between router 2 and router 3, so I'll make this 2, 3.
That's right.
Yes.
How have you typed that?
Typed what?
Those numbers there.
Really?
Yes.
And your question be more specific? I'm typing by pressing buttons on my keyboard.
No.
No.
That's what I mean by be a bit specific. Your question is very blunt. How are you typing those numbers?
Okay, how? I don't know.
Okay, the tools you used for typing.
This one.
Okay, I've seen.
Yeah, I clicked on this and did this, and then I typed.
My buttons.
Yes, you know, when you're doing technical stuff, you need to start asking things that are a bit technical. Now, when you say, how are you typing, and you tell people you're studying network engineering and they are listening, you understand me? And I get confused, like, how are you typing? Why I'm confused? Please don't misunderstand me. It's because I have also told people who are complete beginners, okay? So sometimes people ask questions and they mean the real basic thing. And then you explain the technical one. Then the person is like, okay, I've understood. But you've just confused them even more.
You've understood.
Okay, cool. I'm using this, I think, I don't know if I guess, for some people, when they ask me that question, they don't actually mean this. They mean there is this thing I do and people think it's complicated. After typing one of these, I copy it and paste it and I move it to another network and I just change a part of it. If that is what you meant, then it's also that. I just copy, Ctrl-C, Ctrl-V, and then I put it somewhere else and rename it.
Okay.
Just in case. But again, I like questions. I like people who ask. It shows people are watching what I'm doing. And for me, that is a good thing. So this is going to be 10.0.1.0 because it is connected on only router 1. This is 10.0. So all of them are 10.0. The number here is based on what you're connecting. This link is connecting router 1 to router 2. This one is connecting router 2 to router 3. You guys understand, right?
Yes.
This one is only on router 3. So it makes it also easier for me, but I use this only when I'm doing labs, my own labs. It is easier to remember which network I'm configuring and to memorize the networks than if I just got some random numbers from nowhere. So after doing that, I'm going to open let me start with these PCs. I'm going to call this PC, PC1. Sometimes it auto numbers them in a way you don't want. So I like numbering them myself. This is PC2, this is PC3 and PC4. The other thing I like doing when I'm doing labs, I connect the PC to an interface on the switch that matches its number. I've not done that here. But I like connecting PC3 to interface 3 and PC4 to interface 4. PC1 to interface 1 like that. That way I can easily know what I'm doing. I'm not doing that here because I'm not going to configure any port security, no STP, so I don't need any specifics about ports. So I didn't need to do that here. All right, so I'm going to start these 3 routers only. I'm starting each of them alone because if I click here, it will open also switches, which I don't want. So I'm going to, let me put this down here. I've not finished the labeling, sorry. This is going to be, now you see, I'm going to give these ones IP addresses that match the PC number. So this is going to be .1, this is going to be .2, I hope you guys understand this procedure. It makes your work much easier when you're configuring. This is going to be .3. This is going to be .4. Matches the PC number. Now I'm just going to use a rule of thumb that both routers are .10. Both gateways are .10. Why am I using .10? I just decided to use .10. You can decide to use .254, .200. Just don't use .500 because it doesn't exist. Now for this one, I'm going to use the router number, .1, here. Actually, let me change this also to be .1, but .1 is already here, so I can't do that. And then I'm going to use .2 here because it is router 2. Okay, and I'm going to use .2 also here because it is router 2. So I'm going to use, I would use .3 here, but I can use .3 here. Right. I was going to say I have used it already here, but this is a different network. I hope we are together.
Yes.
So I'll start with PCs. This is going to be 10.0.1.1, 255.255.255.0. The default gateway is going to be 10.0.1.10, which is the interface of the router. Is everyone with me?
Password, how have you brought these things?
I double-clicked on this computer like that. Yes, and I'm under basic config. Later on, I will go to command to ping.
Yes.
Okay, so I will open this also and type in 10.0.1.2 and then the subnet mask 255.255.255.0, 10.0.1.10. The default gateway is, or the gateway is the interface on the router. Then I'll go to PC3, it's 10.0.3.3, 255.255.255.0, 10.0.3.10. We are together?
Yes.
Yeah.
Finally, PC4 will be 10.0.3.4, 255.255.255.0, 10.0.3.10. Done. Now, just to confirm, I'll try to ping from PC1 to PC2. Ping, because these ones can communicate even without the router. Okay? It's layer 2. Ping 10.0.1.2. Cool. So my configuration so far they are good. Now I don't need to ping back because when this ping succeeds, it means it sent and received a reply. Are we together?
Yes.
So I will also ping 10.0.3.4 from PC3, and I have the ping going through. All right, PC configuration is okay. I'm not going to configure anything on the switch. Let me just rename this to switch 1 and also rename this to switch 2. Excuse me, to switch 2. And then I'm going to come to the routers now and do the configurations. On each router, I'm going to configure 2 interfaces. This one .10 and that one .12.1. This one .12.2, this one .23.2. This one .23.3, this one .3.10. So I'll start with the Kampala router, I'll go to the Mukono router, I'll go to the Jinja router. Is everyone following with me?
Yeah.
Yep. Yeah.
Okay, so go to system view and then change the name of the router to Kampala router. That's it. And then I'll go to the interface gigabit Ethernet 002 and give it the IP address 10.0.1.10/24. I'll go to interface gigabit Ethernet 000 and I'll give it the IP address 10.0.12.1/24. Done. Just to confirm, I like displaying IP interface brief. It shows me 10.0.12.1 on 0. Yes, 10.0.1.10 on 2. Cool. Then I'll go to the Mukono router. System view. System name is Mukono router. And then I'll go to interface gigabit Ethernet 000. and I'll give it the IP address 10.0.12.2/24, and I'll go to interface caption 001, and I'll give it the IP address 10.0.23.2/24. Just to confirm, I'll display IP interface brief, and I have gigabit and 000 10.0.12.2, cool, 10.0.23.2, cool, right. And from here, I will go to router Ginger and go to system view and change the name to Ginger router. And then I'll go to interface gigabit Ethernet 001 and type the IP address as 10.0.23.3/24. I'll quit out of that and go to interface gigabit 002 and give it the IP address 10.0.3.10/24. Cool. Display IP interface brief, just to confirm, 23.3 and 3.10. That's cool. Now, I want to see whether routers can communicate among themselves. From Kampala router, I'm going to ping Mukono router, this interface, because they are directly connected. I'll ping 10.0.12.2, and sure I have replies, that's great. I'll go to the Mukono router and ping the Ginger router. I'll ping 10.0.23.3 and see, cool, they are communicating, that's great. Now I'll go to the host and try to ping the default gateway, ping 10.0.1.10. I can reach my default gateway, that's great. And I'll go to this host one of these two and also try to ping the default gateway, ping 10. This is normally important. You don't want to start looking for mistakes after you've configured routing. That's great. Now I'm going to go on PC1 and try to ping 10.0.3.3. I'm pinging PC3. What do you expect to see?
It will not reach it.
It will not reach it. It will not reach it. Why? Let us confirm. You see? Timed out. Timed out. It is sending the packet to the gateway. Let's confirm that. Let us capture packets at the gateway interface. Let us capture packets at the gateway interface. I take long in this lesson because it makes my work on routing protocols easier. Let us capture packets at the gateway interface. This is our Wireshark. I'm going to first put it down here, and then I'll ping again. Excuse me, excuse me, excuse me, excuse me. This is my Wireshark. This is my window. I'm going to ping again from here, and we see. You see? It is receiving ICMP request, but it's not replying. You see that? Request, 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 no replies. Request, request, no replies. Are we together?
Yes.
Cool. Let us see whether this router is sending out these pings. Let us capture packets here. Let us see whether this router, are you guys getting what I'm doing here?
Yeah.
Let us see whether this router is sending out these pings. So I'm going to put this here and get my window for pinging here, and I'll ping again. You see, this guy is not sending anywhere. Have you seen that?
Yes.
He's not sending anywhere. Why isn't he sending? Let us see this router's routing table. The destination network is not there in his routing table. Is there anything like 10.0.3.0 here?
No.
You see, this network, 10.0.3.0, is not there in the routing table. So the router doesn't know anywhere to send the traffic. Are we together? Now, I need to tell this router that if you receive packets for 10.0.3.0, send them to this interface. And then I'll come and tell this one that if you receive traffic for 10.0.3.0, send them to this interface. Are we together?
Yes.
Now, this one, on the other hand, display IP routing table has it as a directly attached what? Route. Are we together?
Yes.
But this one does not have it. Display IP routing table. It does not have it. So I need to tell this one that, hey, IP route static, if you want to send to 10.0.3.0 with a 24 subnet mask, send to 10.0.12.2. I've done. Let us display the IP routing table again. Have you seen that? If I try to ping again now, we shall see that this router is sending the packets out. But when they reach this one doesn't send. So we are going to come here and also tell it, hey, in case you want to reach 10.0.3.0 network with a 24 subnet mask, send to 10.0.23.3. So now if I display IP routing table on this again, it also has a way to reach that network. Now, both routers know how to reach the network. Can we now ping?
Yeah.
Just to confirm, let me capture packets here. Let me capture packets here. Just to confirm that the routers know where to send, I'll capture packets here. Okay? So I will then ping. You see? It started with an app. Who is 10.0.3.0.3, sorry, tell.3.10. You see? Request goes, reply comes. But meanwhile, decide what is happening.
Timing out.
It's timing out.
Why? We have seen this guy is sending the request. This one is even replying. What is happening?
We need to set the routes for the reply.
This guy is replying, but look here closely. The reply is going to 10.0.1.1. And this router, display IP routing table, does not know of the network 10.0.1.0. So we need to tell this router how to talk back. If you have anyone who is going to 10.0.1.0 network, send to this interface. And we shall also tell this one, if you want to have anyone to go to 10.0.1.0 network, send to this interface. That's what I'm going to do now. I'll go here and say, hey man, if you want to send anything to 10.0.1.0 with a 24 subnet mask, send to 10.0.23.2. Display IP routing table. You see that he now has a way to send to that network. Then I'll come to, then I'll come to the Mukono router and say, first of all, we can say it's not 10.0.1 in its routing table. So we shall come and say, hey, man, if you have anything to send to 10.0.1.0 network, the 24 subnet mask sent on 10.0.12.1. If I display IP routing table again, we can see he now knows how to talk back. Now, ladies and gentlemen, if we ping, we should be able to receive replies. But you see the first packet times out. Why? Because the router is checking its routing table. It's checking its routing table. So you can see, finally, there is what? Communication in our network. That's how static routes work. Are we together?
Yeah. So John.
Yes.
if we are trying to edit our routing table, that means if we are trying to instruct router Kampala to send packets to router Mukono, the same thing to router Jinja.
Yes.
The same way, if we are going to have the reverse routing, it should start from Jinja to Mukono to Kampala.
Yes.
Okay, fine.
I don't know whether I've understood your question.
I'm meaning in terms of the sending, the directives of sending the packets.
Yes.
From router Kampala to Mukono to Jinja. The same way, if you want to get the feedback, you should instruct Jinja to also send back from Jinja to Mukono to Kampala.
Yes. We could actually tell this Jinja router to send to this interface. But does Jinja router know this network? He doesn't. So we shall first need to tell him how to reach this network in the first place by sending here. Are we together?
Okay, fine.
Yeah. Now, you realize in our network that everything the Kampala router needs, this is typically for small enterprise networking, where you buy one router and then the internet service provider connects to that router. Okay? Instead of telling it that to reach this network, you want to tell it that to reach any network, send to this next door. Are we together?
Yes.
For example, on this router, let me show you something interesting. You see here, I have got a way to talk to PC3 and 4. Just to confirm, let me ping 4. You see? Since we can reach 4, we should be able to reach the router Jinja. Don't you think so?
Yes.
Yes?
Yes.
Let's see. Now what's the problem? Do not forget, guys, routers do not understand. They are not looking at this screen. They don't see things the way we see them. The only thing they use is their routing what? Does it have anything in it for the 23.0 network?
No.
No. So it can't reach here. All it was told that if you want to reach here, send your nonsense here. That's it. So sometimes you want to tell it that not just here. If you want to reach anywhere, just send the packets here. Now that is going to bring in our any network address. We are going to say IP, route static. If you want to go to any network. Are we together?
Yes.
Together.
Yes.
For sure, this class can be boring sometimes. Most times I should add, with any subnet mask, send your packets to 10.0.12.2. Now, when we type this command, what we are saying is that for any destination, remember, for the previous command we typed, if you remember, we said to reach the .3 network. Now, this is not a .3 network. That's why we can't reach here. But with this new command, we are telling it to reach any network. Just send to that next door. This type of route is what we call a default route. We are going to see what it displays like in the routing table. Display IP routing table. You see the route? Any network with a 0 subnet mask. This one will only be used if the route is not there anywhere else. Are we together?
Yes.
And then we shall also come to this one and tell it, in case you want to reach anywhere with any subnet mask, send to 23.2. Display IP routing table. See, it's here. Now, with that one, whether I ping here, whether I ping here, whether I ping, it is going to reach, because I've given it a default what? A default route. Are we together?
Yeah.
It is normally used in cases where you have one router connecting you to the internet. So whether you're connecting through the internet to another branch, or just to the internet, or just to who, it is still that same router taking you out. So you just set up a default router and say, if you want to reach anyone, just send it to. Now that default route for most of our Soho routers, small home office, small office, home office router, Soho, they will only have that default route to send them to the ISP router, and all the communication will work like magic. And those default routes sometimes install themselves automatically when you configure the IP addresses. When you connect a cable to the one port, it puts a route to the other end of that cable. Says, no, if you have anyone to anywhere, just send out of this interface and everything will work. But if you want to get gritty with your stuff, you might want to get to control what is happening, and that is what you do. Are we together?
Yes.
Yeah.
Now, as we said earlier, the problem with this kind of configuration is what happens if we change this network? This will still be knowing of that network, and this one will be knowing of that network. We need to open this and manually reconfigure. Which is the better way? The better way is using IP routing protocols. So I'm going to undo the, if you want to send, I'm going to undo, wait, I'm on Mukono router. I'm going to undo, if you want to send traffic to 10.0.3.0 with a 24 subnet mask, and I'm going to undo if you want to send traffic to IP route static 10.0.1.0 with the 24 subnet mask. They are out. If I display the IP routing table again, those static routes are no longer there. I'm going to do the same on the Kampala router. I'm going to undo the IP route static 10.0.3.0 and I'm, /24, and I'm going to undo the IP route static static 0.0.0.0/0. All right, display IP routing table. The default route and the static route are not there. I'm going to undo IP route static 10.0.1.0/24, and I'm going to undo IP route static 0.0.0.0/0. Cool. Display IP routing table. It's not there, so I've removed them. There is no communication now. See? There is no communication. I'm going to use a dynamic routing protocol. I'm going to explain it after using it. We shall do the explanation after seeing how it works here. So I'm going to say OSPF1, area 0, OSPF1, and then I'll go to area 0 of the process, and I'll advertise the network 10.0.1.0 and I'll also advertise the network 10.0.12.0 We shall understand what this is. Don't worry about it for now. But this is basically how dynamic protocols work. And then I'll say OSPF1 area 0, and I'll do the network 10.0.12.0000255, and I'll also do the network 10.0.23.0000255. Basically, every router advertises the networks it knows of into OSPF. So I'll do OSPF 1, I'll do area 0, and I will enable network 10.0.23.000.255, and then I'll also do the network 10.0.3.0.000.255. That should be good to go. Only that I'm not seeing the process complete. Okay. Now, display OSPF here brief. I have neighborship with .2, but it's stopping at 2-way. This is not supposed to stop at 2-way. Yeah, it's now complete. Cool. And then I will display OSPF here brief, and I have neighborship with .2, and it's full. Cool. Now I'll display the IP routing table, and you can see that I've learned of a route to the .3 network, and the metric, the preference is 10, the metric is 3. Preference is 10, metric is 2. Okay? I have learned about these networks already. So you see how dynamic ones work? It's much simpler. I don't have to go there, configure it out for coming back, configure it out for going, configure it out for reaching the middle. Now I can ping here, ping here, ping here. I can ping anything here because OSPF has done its job. Excuse me. I can display OSPF routing table, and you can see it has a number of link state adverts. We are going to look at details of that, but basically this is how OSPF routing or any dynamic routing protocol works. It generates the routes, it discovers alone. What I've just done is telling this router, hey man, I want to be sending OSPF hello packets here. Let me capture for you here data, and you see. It is sending hello packets. Hello, anyone who knows about OSPF? Anyone who is part of OSPF? And here I can also speak OSPF. You see? You see? It sends hello packets. It sends, this one came from .2. It went to a general, this is a multicast address. If you remember 224, something, multicast range. And then it is also receiving, okay? It sends from itself, which is .2, sends out there. Anyone who speaks OSPF, this is my hello packet. What's there in the hello packet? The hello header, you see? Me, I'm working with OSPF version 2. This is my hello packet. It is 48 bytes long. I am the one who sent it, and I'm in the area 0. My checksum is okay, it is checked. And then what is exactly the information? It advertises its own subnet mask, and then the hello interval. Now, if anyone else agrees with these things, they set up an OSPF relationship. We are going to look at OSPF in detail. But what am I trying to say? What I'm trying to say here is, what I've just done here is telling this interface, where you're part of OSPF, okay? I tell this one also, hey, you're part of OSPF, okay? I tell this one on this router that this interface is part of OSPF, this one is part of OSPF. I come to this one, I say, this one is part of OSPF, this one is part of OSPF. Now, what's the magic with that? This one says, hey, out there, I'm part of OSPF. This one also says, hey, out there, I'm part of, and then the hello messages reach. That's how, once they meet and they agree, that's when they set up this OSPF neighborship. Say, oh, so I have a neighbor. It says meeting you. I've been down, but let me start initializing myself to set up a relationship with you. Now, since I've been initialized, now I'm going to go to 2-way, since you're also ready to initialize a relationship with me. Are you really okay? Are you sure about this? Oh, cool. Then let's get to 2-way and even start exchanging information. They start exchanging information. I have this network connected to me. I have this network connected. They load, and they go to full mode. Now they are real adjacent neighbors. Now, this happens with all different links. This link sets up relationships. Once you become neighbors, this one starts telling you, oh, by the way, I have one child and 2 side dishes and 3 rooms and what. They tell you everything about them. You receive it, you tell that guy because you formed a relationship with him. He also tells you his stuff. Oh, you know what? I have 1 wife and 2 side dishes and 2 children. And you know, you all exchange everything. And before you realize, you all know everything. So when I display OSPF routing here, what I have here is exactly the same with what this guy has. When we check his display OSPF routing, it is exactly the same thing he has because we have all exchanged our information and so all routes are reachable everywhere. That is how dynamic routing protocols work. Okay. So I've used ENSP itself live to show you about this slide, how dynamic routing protocols work. This one, I don't need to say anything more about it, and we have seen how static routing protocols work. And now we have a number of dynamic routing protocols, routing information protocols, open shortest path first, intermediate system to intermediate system. And then we have BGP or border gateway protocol. These 3 work internally to an autonomous system, a system of layer 3 devices under one administrative control. This one is the one that connects different systems, different administrative controls. It is an exterior gateway protocol. These ones are all interior gateway protocol within the same system. And then we can even classify them by the working mechanism or working algorithm. And here we have what we call the distance vector or RIP, routing information protocols. It uses distance. You know, when I told you are thinking RIP, am I even online?
Yes, you're online. We record.
So you're just stubborn. Okay. All right, so when I told you are thinking RIP, how RIP calculates its destination is that for it, it simply counts the number of hops. Hop 1, hop 2, hop 3. So if there is another path that reaches the same destination, hop 1, hop 2. RIP will always take this path, says this one is nearer. There are just 2 stops along the way, okay? It uses the distance vector. It counts the hops. That's routing by rumor. Now, OSPF says, okay, this one, fewer number of stops. But how fast is the bus? What speed is it taking? What speed is it taking? In this case, it is the bandwidth. OSPF will consider also the bandwidth on the network. So this is how we classify. OSPF and ISIS are called link state routing protocols. We are particularly going to talk about OSPF as we go on. I told you about route recursion already. Route recursion, a case where the next hop, for example, to that network, to this network, the next hop is this one. What happens in that case? The router checks its routing table and sees the next hop is this one. But the next hop is not also directly attached. It has to search the routing table again to see the path to the next hop. Do you guys understand?
Yeah.
Yes.
Yeah, this is what it does. So to reach that network, go to that next hop. Then it does recursion. Checks the routing table again. Oh, now to reach the next hop, go to that interface. Then it sends to that interface, that one sends to the next hop. I hope that makes sense. And then we have what we call equal cost routes, where you have two different routes with the same cost. What is going to happen in that case is load balancing. When we get two packets, we shall send one there and one there. Another two, one there and one there. That's how we shall communicate. It's called load balancing. And then we have another concept of a floating route. That one is better done than said, but basically, I'm not going to do it. I want to give you a break. Basically, what is going to happen? Oh, no, can we discuss this after the break?
Yeah.
Yes.
Okay, cool. Let's get a break of 15 minutes. Huh?
Yeah.
Pardon?
Some of us were not home. If you give us a break of 20, yeah?
By not home and a break of 20, how do those two apply?
Definitely, I'll have to jump somewhere, pick a bite, then come back.
But now someone else will say for me to go for where I'm supposed to get that something, it's taking me 15 minutes. Ultimately, you'll ask for a break of 1 hour.
No, not really.
Okay, so what I've done, I've set up this network here. I've put this PC here with the IP address 10.0.1.1 and its default gateway is 10.0.1.10. I've put one link here with the network 10.0.12.0 with .1 that side and .2 this side. And I've put the second link 10.0.1.2. Sorry, 20.0.12.0 with .1 this side and .2 that side. This PC has the IP address of .1, 10.0.2.1, and the router, the gateway for this PC, as you can see, 10.0.2.10. I've already done all the testing, pinging, and everything is okay. And what we want to see is the routing table of this IP routing table. Look at this routing table. We need to set up a route from this router to this network, and we are going to choose a next hop. Now, I need you to be with me. There are two next hops, and both of them can lead us here. Which one should we use?
.0.1.2.0.
Okay, cool. So we are going to say IP route static. In order to reach 10.0.2.0, the 24 subnet must go to 10.0.12.2. Done. And then we shall go to router 2 also and say IP route static and say if you want to reach the 10.0.1.0/24, send to 10.0.12.1. Are we together?
Yes.
Cool. So now what is going to happen is I can ping 10.0.2.1. I should be able to ping it, right? See that? All information is taking the upper link. Okay? What happens if we enable this also? What happens if we set up another route if you want to reach that network sent to this next hop? Let us first see a routing table here. Display IP routing table. You see, we have that destination. What happens if we add? What happens if we add IP route static? If you want to reach 10.0.2.0, send with the 24 subnet mask, send to 20.0.12.2. What happens to our routing table? Display IP routing table. Do you see, for the same destination, we now can send to 10.0.12.2 or 20.0.12.2. And they are both showing in our routing table, meaning there is going to be load balancing. Are we together?
Yes.
Yes.
We can also add here the second route, that if you want to send to 10.0.1.0 with a 24 subnet mask, send to 20, send to 20.0.12.1. That display IP routing table, and you see for that network we are going to do. Now, in most cases, this is not what we want. In most cases, we want one of these routes to be our backup. Are we together?
Yes.
Yes.
We want to use the upper link, but if it fails for some reason, we switch to the lower link. We don't want to be using both links. Are we together?
Yeah.
Now, in that case, we are going to get hold of our second link and make it a backup. What we are simply going to do is to manipulate its preference. We are simply going to manipulate its preference. We are going, let me first remove it. Undo IP route static 10.0, no, it's 20. The second one is 20.0.12. Excuse me, 10.0.2.0 with a 24 subnet mask. The one with the next top of 20.0.12.2. We remove it. Now display IP routing table, it's no longer there. See that? We are going to remove it even here. Undo IP route static. The one to 10.0.1.0 with the 24 subnet mask. The one whose next top is 20.0.12.1. Remove it. Now, if we display the IP routing table again, you see we no longer have the second one. Now, what we are going to do is to put back the second one. Pay attention here. We are going to say IP route static to go to 10.0.2.0 with the 24 subnet mask, send to 20.0.12.2, and we are going to change the preference. For the preference, use 80. We know that the default preference for static routes is 60. Are we together?
Yeah.
But for now, we are putting back a static route and giving it a preference of 80. I'm going to hit enter. Bam, it's there. Display IP routing table. It doesn't display anywhere in the routing table. Why? Because when we were looking our best path selection, we saw that the one with 60 was the best path. So we hid away the one with 80. It is there, but it is hidden. Are we together?
Yeah.
So I'm going to do the same here. I'm going to put back IP route static. If you want to go to 10.0.1.0, 24 subnet mask, send to 20.0.12.1, but set the preference of this one to 80. It's now inside. If you display the IP routing table, it is not there. Why? We have selected the one with preference of 60. Just to confirm that it is there. We know the one with preference of 60 is taking the upper line, isn't it?
Yes.
I'm going to come to this router and kill this interface. I'm going to shut it down. This one, .2/002. I'm going to shut it down. Are we together? Someone with me in class?
Yes.
Yes.
You see the route we have is 60. I'm going to shut down this interface. And then I will open this routing table again. Shut, right? Display IP routing table. Do you see? A new route has come with a next top of 20.0.12.0. And again, if we ping, we shall have success. If we ping, we shall have success. 10.0.2.1. We shall have success. Because we are now taking the other route. Are we together?
Yes.
That kind of route is called a default static route. Now, if I bring back this interface, everything works automatically. If I bring back this interface, this route of 80 is going to disappear from the routing table. As soon as the interface goes to the app state, if I display the IP routing table again, we are going back to our original line because it is easier to reach there. We trust it more. It has preference of 60. We install one route to the routing table. We only install the best one. There are normally always other routes, but we install only the best route unless there is equal cost routes. If they are not equal cost, we shall only select the best what? Best route. Are we together?
Yes.
What I've just done is setting up what we call a floating static route.